Welcome to our transaction management module. In this module, we will start talking about transactions in a relational database management system and set the foundations for our discussions about concurrent transactions, as well as recovery of our database management system from failures. What is a transaction? A transaction is a sequence of one or more database management system operations, such as a read or a write, which reflects a single real-world transition that performs a single logical unit of work. It is also defined as a single run of a user program in a database management system. For example, transferring money between two accounts is a transaction. Purchasing a group of products is a transaction. Or registering for a class is also a transaction. As we have already briefly discussed in Module 1, properly implemented transactions in a relational database management system ensure maintaining ACID properties of a relational database. ACID states that a transaction should be atomic, consistent, isolated, and durable. ACID properties have been subject of many historic and current conversations. NoSQL databases relax ACID properties by adopting eventual consistency. NewSQL reintroduces ACID compliance to NoSQL-style database management systems, though. Before diving in how to ensure these properties in our transactions, let's quickly review their definitions. Atomic is the all-or-nothing property, meaning that the transaction should either execute completely or stop completely without having any effect on the database. A transaction on a relational database management system should be atomic, executing completely or not at all. Therefore, there are only two possible outcomes for an atomic transaction. It commits, meaning all the changes in the transaction are made, or it aborts, meaning absolutely no changes are made. For example, assume we have a banking transaction to transfer $100 from an account 123 to the account 456. We have a relation accounts, which account number and balance are parts of it. There are two steps in this transaction: adding $100 to account 456 and deducting $100 from account 123. So, what happens if we stop after step 1 shown here, but before step 2 is done? We have created $100 on the fly. Atomicity ensures we either do both of such steps, which are part of one transaction, or neither of them. Consistent refers to the integrity and consistency of the database that should be maintained by each transaction. Consistency property for a database states that the tables must always satisfy user-specified constraints. This includes attributes and tuple integrity on domain, key, value, and business constraints. For example, a bank account number should be unique because it is defined so by business requirements and maintained in a relational database as a key constraint. Stock amount kept, bought, or sold cannot be negative, and sum of debits and credits of an account should be 0. Database programmers make sure a transaction takes a database from a consistent state to another consistent state. As we will see, with consistency achieved for one transaction through programmer-defined states for a database management system maintains this consistency by ensuring atomicity and isolation. Isolation means that each transaction should be executed as if there are no other transactions executed at the same time. but we know that a transaction can potentially execute concurrently with many other transactions. Isolation means ensuring that the effect of the concurrent transactions is as if each transaction executes in isolation from the other transactions. This means neither of the transactions should observe changes from other transactions during its run. For example, say we have flight reservation service, which is maintained by a flights database. What happens if two transactions reserve the same seat at the same time? What happens if more than one person has the same request at the same time? Do we show both of them the available seat? Do we book the available seat for both of them? Isn't that double booking? So what happens? Double booking cannot and will not happen. This is ensured through isolating the concurrent transactions. We will see later how. Durable means that once a transaction is committed, its effects after the completion should remain in the database. The effects should continue to exist after the transaction, even if unexpected events happen, even after the whole program terminates, even if there are power failures, crashes, and events of the sort. We still want to make sure that we do not lose the data that is supposed to be stored in our database. The first implication of this is the fact that the data should be written to persistent storage, followed by the need for mechanisms for recovery when failures happen. In database management systems, we face two big problems that involve asset properties that we just discussed. The first problem is supporting multiple transactions at the same time. This might become a challenge in databases with large number of concurrent transactions. For example, in the airline reservation system example we saw, we do not want to end up double booking a seat to two users because their transactions were happening at the same time and both started when the seat was available. So we have to make sure we effectively handle supporting concurrent transactions. And the second problem is making sure the data stored is reliable. Whether a crash, a temporary loss of electricity, or failure of a system, we want to ensure our database ensures to hold the record once it is committed. Note that these two problems arise from the challenges in maintaining asset properties during our database transactions. In a database management system, our first problem is addressed by concurrency control mechanisms. These mechanisms ensure maintaining consistency and isolation properties. The second problem is addressed by database recovery mechanisms that ensure maintaining atomicity and durability properties. This defines the structure of our discussions in this module. We will first discuss basic background on concurrency control and database recovery. We will then continue on this module, concurrency control and how it maintains consistency and isolation. In the next module, we will discuss database recovery and how it maintains atomicity and durability.